So we are looking at the fundamental theorem of calculus. So there's some big ideas in calculus, and one of them is this idea that it's not just calculus, but in math, that everything has an opposite. So times and divide are opposites, add and subtract are opposites, squares, square roots, sine, arc sine are opposites. When we want to do something in math, we can often undo it. Okay, so finding a slope function, so differentiating, should be able to undo that. So go from a slope function to its antiderivative function. So that's a big part of fundamental theorem of calculus, this idea, and just it's connecting to this big idea in math that everything has an opposite operation. We can undo things. So in calculus, we can find slope by finding the derivative, and we can also find area under the curve. And those two operations are essentially opposites of each other. Okay, and so we're going to undo things using the fundamental of calculus, and we want to try to relate it to this idea of area under the curve and slope. So the main part, there's two parts to it essentially. The main part, one part of the fundamental theorem of calculus is that if we take the integral of something, okay, so that is the antiderivative essentially, and we're not going to pay attention too much to notation right now, but this idea, well, I'll get back to that, but this idea of finding the integral or the area under the curve, we can differentiate and get back to the same thing. Okay, and the opposite is true as well. If I differentiate integrate a derivative, okay, I can get back to the original function. Okay, this is the fundamental theorem of calculus here. If we differentiate the integral, we end up back to where we started. Okay, so basically the integral and derivatives are opposites. Okay, this idea of add and subtract being opposites. So we can also connect this to the idea of area. Okay, so when we talk about the area underneath a curve, so if I take a look at this curve f of x and I multiply it by dx, I find the area under that curve, the area of each one of those rectangles. I sum up that area, that's the total area under the curve. Well, that area under the curve happens to be the displacement on the antiderivative function, and vice versa. So I can calculate the displacement on the antiderivative. That gives me the area underneath this curve. The area underneath this curve is the displacement on the antiderivative. Okay, so that's the second part of the fundamental theorem of calculus. Okay, so we go back to this idea of area of a curve. And we can go back to this, and we can actually look a little bit closer at the notation of this first statement. And we can say this. Okay, so we know that the area underneath this curve, we look at that as area. We can just kind of say this. We have some curve. We're going to call this curve f. That's our f of x, or in this case, it's going to be f of t. And we're going to just set some arbitrary starting point a. That's our lower bound. And we're going to set, so that's a fixed point. And then we're going to have some variable point x. And this x can kind of move around. And wherever that x stops is going to be the area underneath the curve. Okay, and so the area underneath the curve essentially is giving us a function, okay, which is calculating this area. Okay, so this is the where this x stops is the area, and that's essentially the antiderivative function. We'll call that the area function. So that's our area function, and what we're saying is that the area under that curve, okay, if I work it out using my antiderivative here, okay, so I'm going to just anti-differentiate this. It would look like this. I know that the area underneath this curve must be, okay, I'm going to go f of t dt from a to x, and the area underneath that curve is going to look like this. It's going to be, oops, where did my thing go? I just lost my, Okay, so the area underneath the curve is going to be based on this difference on the antiderivative function. So it's going to be f of a, big F, minus big F of x. Okay, and really we can put our plus c in here if we want, plus c, and minus, or sorry, it's going to be x here, and we're going to have our big F of a. We don't really need the plus c, but we'll just leave that in anyways. So there's our derivative, or antiderivative. Okay, and that's calculating the area underneath that curve. Right? I'm just going to actually take out that plus c because we don't really need it. F of a, there we go. Okay, so that's going to be our function here. I'm going to put brackets around that because what the fundamental theorem of calculus is saying is that if I differentiate this, okay, so if I differentiate this, I should end up with my original f of x, and which I do. Okay, because if I differentiate this, I'm going to end up with the derivative of big F, which is f of x, minus the derivative of f of a. Well, this happens to be a constant, so that's going to end up being 0. So there it is. There's the first part of the fundamental theorem of calculus. And we can establish this using this area function, essentially. And calculating the area, we can look at it in that way, and we can just establish, oh yeah, we're going to essentially, if we do our derivatives and all that we learned, we're just going to end up with back to where we started, okay, which is f of x. Okay, so that's a big idea, and these two parts are kind of the two main ideas of the fundamental theory of calculus. So I'm just going to reiterate them again. The idea is that the integral and derivatives are opposites. Okay, so when we differentiate and anti-differentiate, they're essentially opposites and undo each other. They're not exact opposites when we look at it a little bit later, but they're essentially opposites. The other part of the fundamental theorem of calculus is that the area underneath the curve is equal to the displacement of the antiderivative function. Okay, so the difference in the f of b and f of a. Okay, so where f of a and b represents lower and upper bounds.